Hey everybody, in this video we're going to continue working on explaining properties with intermolecular forces. In this case, we're going to be analyzing CH4 methane versus NH3 ammonia and trying to make a prediction about which of these substances will have the higher melting point. To do this properly, there's a lot of stuff you have to go through. A bunch of these are really fast, so don't feel too overwhelmed, but these are all the things you have to think about when you're answering a question like this. Let's take a look at it. The whole process begins with the Lewis structure and the proper shape of these molecules. I'm not going to go over this part in depth. I'm just going to jump straight to the final result. Both of these guys have a tetrahedral arrangement. But there's one huge difference that's going to matter in a second here, and that is in NH3, one of those positions is taken up with a lone pair. That's going to play a large role in the next thing you've got to think about, which is the polarity of these molecules. One aspect of this is the difference in electronegativity values. I don't know these numbers exactly off the top of my head, although let's see, carbon I believe is like a 2.5. and hydrogen is a 2.1, right? So the difference in electronegativity here is about a 0.4, right? It's there, but it's small. In NH3, it's going to be much larger because nitrogen is a 3.0. It's one of your higher elements, and there we've got a 2.0. So we've got a difference in electronegativity of 0.9. So both of these molecules have electronegativity differences. That means they all have polar bonds. But CH4, if you look at the arrangement of those bonds, they're completely symmetrically arranged around that central atom carbon. So while the bonds are polar, there will be no net dipole here on CH4. In other words, CH4 is nonpolar, whereas here, because we have a lone pair on this top portion of the molecule, there is an asymmetrical arrangement of those polar bonds. So NH3 is a polar molecule. There is a net dipole. And all of that work with polarity is so that we can actually properly list out the types of intermolecular forces that are going to exist between different CH4 molecules and between multiple NH3 molecules. Because CH4 does not have a net dipole, it's a nonpolar molecule, it is only going to have London dispersion forces. It's the only force that nonpolar molecules are capable of experiencing. Ammonia, NH3, it's going to have LDFs as well, because all molecules, all atoms, as long as they've got an electron cloud, are going to experience some LDFs. But there's another one here that's occurring. Because this is polar, NH3 is also going to experience dipole-dipole forces. Even better, these dipole-dipoles will fit the definition of being a hydrogen bond. So that's a huge difference between these two substances that's going to come into play in a little bit. Okay, so now we know what types of IMFs we're dealing with. Now let's start to compare their strength. For LDFs, you have to consider two factors, polarizability and chain length comparison. For these molecules, they are not chain-based molecules, right? They're just one single central atom, so we don't have to worry about chain length, but we can make some rough comparisons about polarizability. And the good news here is that there is no major difference in polarizability. Maybe I'll just summarize that by saying similar polarizability for both, and that's because the outer atoms on both of these molecules are hydrogen, which have the the same electron clouds. There's not one larger electron cloud than another. The central atom, carbon and nitrogen, both of these elements are in the same row of the periodic table. They're going to have electron clouds that are similar in size. Whatever differences there are between carbon and nitrogen, because they're in the same row of the periodic table, they're going to be very minor differences. I'm not going to have to worry too much about whatever those differences in polarizability are. And now that I've done that, I have all the factors that I need to actually compare the strengths of the intermolecular forces that exist between these molecules. Let's start with the dipole-dipoles. This is a nice easy one because CH4 doesn't have them, right? There are literally no dipole-dipoles, so it's a little bit silly feeling to categorize ammonias as stronger, but technically they are because they exist. You know what I mean? First of all, they're hydrogen bonds, which by definition are very strong, but CH4 doesn't have any. So NH3 wins that battle. As far as the London dispersion forces, they do both have those, but for that we go back to the polarizability. And remember how we said the polarizability was similar between these two molecules? That means these two molecules are going to also have similar LDF strength. There's not going to be any major comparison there that I can easily make. Alright, we're almost at the end of the line. We are finally in a position to compare the strengths of the intermolecular forces overall. I always want to point out whenever we're at this step of trying to say which molecule will have the stronger forces, if you are making a prediction, which we are, right? That's what this whole question is. You are usually going to assume that any dipole-dipole forces, and that's covered in this little asterisk right here, you're going to assume that any dipole-dipole forces, especially hydrogen bonds, are going to overshadow and be more significant, more important than any LDFs. That's worth mentioning. Now, it ends up not mattering here because these molecules, have LDFs of similar strength, so we don't really have to worry about that. There is only one key difference, and that is the fact that CH4 has no dipole-dipoles, while NH3 has hydrogen bonds. So this is a simple comparison to make. NH3 molecules will have the stronger intermolecular forces, and that of course is the hydrogen bonds. CH4 is going to have the weaker intermolecular forces because all it has are LDFs. And as soon as you know which substance has the stronger intermolecular forces, you can finally make a prediction about the property. In the case of melting points, a stronger attraction between molecules means that the substance is going to have a higher melting point, and that's because it's going to take more heat, more energy to separate those molecules during that process of melting. In other words, you have to break those stronger hydrogen bonds, which is going to take more energy to do. Here with CH4 molecules, the attractive forces are weaker, so it's not going to take as much heat energy to break them. So CH4, our prediction is that it's going to have the lower melting point. So that wraps it up for this video. Thanks a lot for watching.